Hello everybody, welcome back. Today we are going to talk about binomial and geometric distributions. Alright, so we've been talking about probability distributions, and there are some types of probability problems that can be reduced to just two outcomes. For example, a coin flip, or babies being born. Both can be reduced to two outcomes. A coin flip could be a head or a tail, and babies being born could be just a boy or a girl. All right, when this comes up, we use something called a binomial distribution. Binomial distribution, again, bi means two, means that we are reducing our outcomes to just two. So I'll make a note. There are some requirements for a binomial distribution. The first is each trial can only have two possible outcomes, as we discussed. Trial can only have two possible outcomes. All right, second is that there must be a fixed number of trials. All right, number three, outcomes of each trial must be independent. Basically, in a coin flip, just because you flip a coin and get a head doesn't necessarily mean that the next flip you're going to get a tail. Each one has its own probability. And fourth, the probability of success must remain the same for each trial. So again, with the coin flip, our probability of success in getting ahead would be 1 out of 2, no matter what flip you're on, whether you're on the first flip, the 10th flip, or the 12th flip. All right, so let's talk a little bit about notation. P of S, probability of success. When we talk about success or failure as the two potential outcomes, for example, if you're talking about the probability that a boy will be born, the probability of success is that if a boy is born. Doesn't mean a boy is better than a girl, it just means that that's what you're looking for. All right, and the other outcome would be probability of failure. And again, if your question is, what's the probability of getting 3 heads and 4 flips? Failure would be if you did not get 3 heads and 4 flips. Doesn't mean one is better than the other. It just means it is the not being successful in the question that you're asking. Little p is going to be the probability of success in a single trial. Q is probability of failure in a single trial. And Q, that's a terrible Q. Make a better Q. Q equals 1 minus P. N equals the number of trials and X would equal the number of successes. All right. So that is your basic notation. All right, because when it comes to the formula, in a binomial experiment, the probability of exactly X successes in N trials is N factorial over N minus X factorial X factorial P to the X, Q to the N minus X. And this is the general formula that most people use. There is an alternate, get you the same answer. This particular piece looks very similar to what that we studied before. Looks to me like a combination kind of formula. So you could say, or P of X equals NCX times the probability of X times Q to the N minus X. And both formulas will give you the same answer. I probably will use both of them throughout just to show you that you can interchange. All right, so why don't you pause the video, write down your formulas, and when you come back, we will talk about a few examples. All right, welcome back. Here's our first example. A survey found that 1 out of 5 Americans say he or she has visited a doctor in any given month. If 10 people are selected at random, find the probability that exactly 3 will have visited a doctor last month. So this is a binomial experiment because they either have visited a doctor or have not. So there are 2 outcomes. There are a fixed number of trials because we only have 10 people. And the probability is the same for each trial. So let's take a look. So my little p, I'll switch colors. My little p is going to be what? 1/5, because they say 1 out of every 5 Americans say he or she has visited a doctor. My x is going to be 3, because that's what we're looking at, is probability that 3 people will have visited the doctor. My q equals 1 minus p, so that would be 4/5. My n equals 10. So at this point, I think I have almost everything I need to fill in the formula. So I need the probability of 3 is going to be 10 factorial over 7 factorial, 3 factorial. And if you're not sure where those numbers came from, go back and take a look at the formula. Times 1/5 to the 3rd power times 4/5 to the 7th power. All right, at this point, this is worthy of putting into your calculator. So why don't you pause the video, put it into your calculator, and we'll talk about it on the back end. All right, hopefully you put this into your calculator. And we see that if we do the combination, I get 120. If I do 1/5 to the 3rd power, I get 1 over 125 times 4/5 to the 7th power. And when I run all of that through, I get 0.201. So the probability that they visit a doctor in the last month is 0.201. And yes, I would love it if you were to write that sentence out. All right, so let's go to our next example of weighted dice. Or weighted die. So the probability of rolling a 4 is 30%. Told you, these are weighted dice. These are not true dice, so our probability is not going to be our normal. If the die is rolled 10 times, find the probability of rolling exactly 8 4s. Exactly 8 4s. All right, so we need to start picking some things out of the problem. So the die is rolled 10 times, therefore I'll use a different color, use purple. My n is going to equal 10. My probability of rolling a 4, which is the successful roll, is 0.3. Probability of not rolling a 4, which is my failure roll, 0.7. And I'm looking for 8 4s, so my x equals 8. All right, so now that I have that information out of the problem, my formula is P of x equals NCX times P to the x times Q to the n minus x. Why don't you guys pause the video, start putting this information into the formula. All right, hopefully this is the way these numbers went into your formula. And when you run them through the calculator, I got 0.00144467. All right, or you could say 0.14% probability that out of rolling 10 times, you will get 8 4s. Okay, so take a look, check your work, and in a minute we'll go to the next problem. All right, on to the next example. A survey found that 30% of teenage consumers receive their spending money from part-time jobs. If 5 teenagers are selected at random, find the probability that at least 3 of them will have part-time jobs. Now, what makes this problem unique are these words right here. At least 3. All right, so that is going to alter some of the information that we have. The at least 3 means that our successes, our X, is going to either be 3, could be 4, or could be 5. All right, my Rn is going to equal 5. Our probability of success, our little p, is going to be 0.3 because they said 30%. Our Q equals 0.7. And now we have some work to do to put this into our formula. But the difference is that I need to do this formula multiple times. I need to do the probability of 3, the probability of 4, and the probability of 5 because it said at least 3. All right, so why don't you pause the video and why don't you write out each formula and then we'll talk in just a minute. All right, so let's see how you did. For probability of 3, okay, so I have n factorial, so that's 5 factorial, over 2 factorial, 3 factorial, times 0.3 raised to the third power, 0.7 raised to the second power. For the second one, I have 5 factorial over 1 factorial, 4 factorial, times 0.3 to the fourth, times 0.7, to the first. And lastly, I have 5 factorial over 0 factorial, which we know is 1. 5 factorial times 0.3 to the fifth, 0.7 to the 0 power. All right, so why don't you take a minute, pause the video, run these through the calculator, and we'll talk about the answers on the back end. All right, so let's see how you did. For probability of 3, got 0.132. For probability of 4, I got 0.028. And for probability of 5, I got 0.002. Now to get the probability of 3 or 4 or 5, we have to add up all 3 numbers. So probability that x is greater than or equal to 3 is going to be 0.132 plus 0.028 plus 0.002. So why don't you add them up and we'll see how we do. Okay, so the probability that x is greater than or equal to 3, I got 0.162. And there's your answer. As always, we will write a sentence to reflect the context of the problem. All right, but we do also need to know things like how to get the mean of a binomial distribution. So to get the mean, the variance, the standard deviation of a binomial distribution. So the mean, because it's a fixed number of trials, we could say population mean equals n times p, variance, use population once again, n times p times q, and the standard deviation equals the square root of our variance, which also equals the square root of n times p times q. So there are the three formulas we're going to work with. I've got just a couple of examples, and we'll see how it goes. All right, so here's an example of a study on jury selection. And when this example was presented to me, I was told that it was done in an actual town. A population of a specific town, I was not told which town it was, is 80% Mexican American. We want to select a fair jury of 12 people. So the first question we have is, what is our mean and what is our standard deviation? All right, so the probability of success, or option 1, would be if I picked a Mexican American, so I'll say that is P, and I'll say Q is picking someone else. All right, so if P is the probability of picking a Mexican American, our P is going to be 0.8. Our Q is then 0.2. And we're picking a jury of 12 people, so N is 12. All right, so our average, our mu, equals N times P, which is 12 times 0.8, which equals 9.6 Mexican Americans per jury. So obviously we can't have a 0.6 of a juror. So basically what they're saying is, on average, we should have between 9 and 10 Mexican Americans on a jury. All right, so let's try our standard deviation, which is the square root of NPQ, which says, so N times P is 9.6, so I'll just put in 9.6 times 0.2. Why don't you do this calculation, and we'll see how you do on the back end. Pause the video. So I got 1.39. How did you do? All right. So how does this affect our data? Well, a lot of our data is contained within 2 standard deviations of our mean. So much so that some call it our usual data. So it is usual to be within 2 standard deviations of our mean. So if our mean is 9.6, I add 1.39. I also take 9.6 and I subtract 1.39. And most of our data is going to be within those numbers. So the typical jury should have between 6.82 and 12.38 Mexican Americans on it. Again, obviously we can't have 6.82 Mexican Americans, so we can say 6 to 7 all the way to 12 on it. And you might say, why would somebody do a study like this? Well, I do have a follow-up problem. All right, and the follow-up is this. Over a period of time, $870 people were selected for juries from this town's population. All right, so the first thing I want to do is I want to find out what is mu, what is our mean, and what is our standard deviation. Second thing is, what is our usual range? And now we have a definition on usual, so we can use that within two standard deviations. So if n now equals 870, because that's how many people were selected, again, probability of success is 0.8, probability of failure is 0.2. So let's get our mean and standard deviation. All right, so our mean is going to be n times p. So 870 times 0.8. So why don't you take a moment, do that. I got 696. So that is the average. So on average, out of 870 people, 696 should be Mexican American. Our standard deviation is going to be the square root of n times p times q, which is the square root of 870 times 0.8, 0.2. Why don't you take a moment and do that as well? I got 11.8. So our usual data, most of our data is going to be contained around our mean. If we add two standard deviations and subtract two standard deviations, you wind up between 672.4 and 718.6. So What does that mean for us? It means that that's the range of Mexican Americans that should be chosen over the 870 people. Well, apparently, the question was, the reason why this study was done was because only 275 Mexican Americans were chosen for a jury. And this is why it was referred for investigation. So this is how statistics can relate to the law. All right, why don't you pause the video, digest the binomial distribution. When we come back, we'll talk a little bit about the geometric distribution. All right, for the geometric distribution, right, the criteria is very similar to a binomial distribution, so that's why we do them together. The first three are pretty much exactly the same. Each repetition is called a trial. For each trial, there are only two outcomes, success or failure. Third one is trials are independent of each other. Even the fourth one is very similar. So the fourth says probability of success is the same for each trial. However, the fifth one is where they diverge. In a geometric distribution, we repeat the trials until we get a success. And you'll see what I mean when we do an example. All right. So again, number 5 is the one you have to look out for to know the difference between binomial and geometric, okay? All right. So let's do an example. All right, and here's a fairly basic example. Suppose we want to roll a 4 on a 6-sided die. We roll until we get a 4 and then we stop. All right, so let's run through this and see how it turns out. So let's say the probability of rolling a 4 on the first roll is 1 out of 6. All right, the probability of rolling a 4 on the second roll, right? So it means we fail on the first one, so that I have 5, 6. And then I hit it on the second one, so 1/6, which equals 5 over 36. Now here's where we start seeing a pattern. Probability on the third roll is going to be 5, 6, because I failed on the first one. I failed on the second one, but I hit it on the third one, which would be 25 over, I think, 216. All right, so Now we start seeing a pattern, so we try to generalize, because if I wanted to say the probability of rolling 4 on the X roll, now notice if it's on the third roll, I have 2 failures. So I'm gonna go 5, 6 on failure, but I want X minus 1 times, because that's how many times I failed. 1/6 would be my success. All right, so let's further generalize this. If I said P of X equals, instead of saying Q, I'm going to say 1 minus P, which would be our failure, X minus 1 times P. And there is your formula for the geometric distribution. All right, so my mu for geometric distribution is 1 over P, and my standard deviation is the square root of 1 minus P over P. So there are your formulas. Take a moment, write them down. We'll do 1 or 2 examples on the back end. Pause the video now. All right, so here's our first example. Sharpshooter normally hits the target 70% of the time. Find the probability her first hit will be on her second shot. That's what we mean about we go until we get a success. So success is hitting the target. We want to know if her first hit will be on the second shot. My second question is, find the mean and standard deviation of the geometric distribution. All right. So, we need the probability of 2 equals P times 1 minus P to the n minus 1, which equals 0.7, our probability of success, our P, times 0.3, which is 1 minus P, to the first power, which is 2 minus 1, and I got 0.21 for that. So probability that she'll hit on her second shot is 0.21, or 21% chance. All right, so our mu equals 1 over P, which equals 1 over 7 over 10, because 0.7 is 7/10, which equals 1 times, not that, 10 over 7. And I got 1.42 as my mean. So she'll hit the target for the first time anywhere between 1 and 2 shots, typically. My standard deviation, I got the square root of 1 minus P over P, which equals the square root of 0.3 over 0.7, and I got 0.782. So at the end of the problem, you would write, so the probability she will hit on her second shot is 0.21. On average, she'll hit the target anywhere between her first and her second shot. All right. And lastly, in our experiment of rolling a die, on average, how many will we need to roll in order to get a 4? How many times will we need to roll until we get a 4. Well, once I say on average, that usually tells you that you need your mean. So my mu equals 1 over p. So in a true dice, it is 1 over 6, which again would equal 6. So on average, in order to get our first 4, we'll need to roll 6 times. Doesn't mean that we have to roll 6 times every time to get a 4. Just means that that is the average. All right, so thank you for hanging in with me for the binomial and geometric distribution. And hope you enjoyed the video, and I will see you on the back end.